We will now look upon the regenerative gas turbine cycle. So this is a modification of an open cycle gas turbine plant to improve its efficiency. Okay. So starting with the first point, the air enters the compressor at point 1 and leaves the compressor at point 2. After 2, there is some kind of heat exchanger where the air coming out of the compressor gets preheated. Okay, because it is not actually entering the combustion chamber. Before that, it is getting preheated from some source. So I will mark the exit of that heat exchanger as point number 3, and from 3 to 4 we have the combustion chamber, that means where the fuel is ignited to add enthalpy to the compressed air. Okay, so the air and the air fuel mixture leaves the combustion chamber at condition number 4 and enters a turbine. In the turbine, the expansion process takes place and the exhaust gases leaves at a condition number 5. Okay, if the exit condition of the turbine, that means the condition number 5, the temperature of condition number 5 is greater than the temperature of air leaving the compressor, that means if T5 is greater than T2, then we can use this exhaust gas to preheat the air coming out at the condition number 2, right? The temperature of T5 is greater than temperature of T2, then we can use this T5 temperature exhaust gas to preheat the compressed air coming at T2. Okay, for that we are using a heat exchanger, and this arrangement is called the regenerative gas turbine cycle. It is because the exhaust gas coming out of the turbine, we are regenerating a part of it to give a preheating to the cycle itself. Okay, so the exhaust gas coming at condition number 5 is passed through this heat exchanger to reach condition number 6. Okay, so the actual exhaust means since we are considering an open cycle turbine, the exhaust will be to the atmosphere. Okay, so the actual exhaust from the turbine to the atmosphere will be at condition number 6. Let me mark this process in a TS diagram. This is a temperature entropy chart for the process. So here 1 to 2 we have the normal compression process. Okay, here we have the compression process. Then from 2 to 3 I am marking with the red line, and it represents the reheating process. Okay, the preheating process or the regenerative heating process. Then 3 to 4 is the portion where we are adding the fuel energy. Okay, fuel into calorific value energy, or the Q1 amount of our actual heat input to the cycle. Then from 4 to 5 we will be having the from 4 to 5 we will be having the expansion process. Okay, the expansion in turbine, that means this is a process where we are producing the work out from the turbine. Okay, and the compressor we are giving the work compressor, the WC is derived from the turbine work. That means a part of work produced in the turbine is used to run the compressor, and the remaining part, that means the work produced by turbine minus the work used for the running of compressor, WT minus WC will be the net work output from the turbine. That is the useful work we are getting. Okay, so this is the net work, and the amount of heat energy we supplied to produce this will be the heat energy supplied between the process 3 and 4. Okay, so this is what a regenerative Rankine cycle is. You should note that it is possible only if the exhaust from the turbine, that means the condition number T5 is greater than T2. Okay, only if T5 is greater than T2, then we can use the exhaust gas coming out of condition number 5 to preheat the air coming out of compressor. Okay, then we have a term called the regenerator effectiveness. Okay, the regenerative effectiveness is defined as the amount of heat energy actually we have added to the maximum amount of heat energy that was available. Okay, let's consider this regenerator. We know in the regenerator the actual amount of heat added to the compressed air is T3 minus T2, right? This is the air coming out of compressor at condition number 2, and it gets preheated to the temperature of 3. So the actual amount of heat energy which we have added to the compressed air is T3 minus T2. Okay, divided by what was the maximum available energy in the regenerator. The maximum available energy in the regenerator has the highest point at T5, right? T5 is the temperature which was available at the inlet of regenerator from turbine. Okay, so what's the maximum lowest temperature inside this regenerator? The lowest temperature is not T6 because T6 will be higher than T2. Okay, the lowest temperature available in this process is again T2. That means the amount of energy which we have actually added in the regenerator is T3 minus T2. Okay, but the amount of energy which was available was T5 minus T2. If I was able to transfer the amount of T5 amount of heat energy to this regenerative cycle, then T5 would have been equal to T3. Okay, that means if it was a 100% effective regenerator system, then temperature at 0.5 will be same at the temperature of 0.3. Okay, which is just an ideal condition. Usually we have the regenerator effectiveness in the range of 0.7 to 0.9, something like that. Okay, so if the regenerator effective was 100%, we can substitute A is equal to 1. Okay, or in other terms, T3 minus T2 is equal to T5 minus T2, or in other terms, T3 is equal to T5 for a 100% effective regenerator system. Okay, so let me define some more terms which are related to the gas turbine problem solving one. One is work ratio. What is work ratio? Work ratio is defined as the net work produced divided by the total work produced. For example, if we are considering this gas turbine cycle, the net work produced was W produced in the turbine minus the work required to run the compressor. And what's the actual work we have produced? It's definitely the work output which we have got from the turbine. So this is the net work divided by total work produced. Then there's another term called back work ratio. Back work ratio is defined as the amount of energy which you have used in the compressor to the amount of energy which you have actually produced. Okay, in other terms, the work consumed in the compressor divided by the work generated in the turbine. Okay, then usually in gas turbine problems we will define a term called the isentropic efficiency. Isentropic efficiency. Okay, let me mark the actual processes for compression and expansion. 1 to 2 represents the isentropic compression process. Okay, but in actual compression process, the process will be deviated like this, starting from 1 and let's say a point called 2 dash. This will be the actual outlet point of the compression. Okay, so the isentropic efficiency for a compression process, only for a compression process, is defined as, for a compression process it is defined as the isentropic work divided by actual work. Okay, so that the numerator is always a lesser quantity. Here if you are considering the compression process, isentropic work is equivalent to T2 minus T1 and the actual work is T2 dash minus T1, so that the numerator will be a lesser quantity. Okay, so for compression we will define the isentropic efficiency is equal to T2 minus T1 divided by T2 dash minus T1. Okay, on the inverse, for the turbine the actual process will be divided like this. Let's say this point be 5 dash. Okay, here 4 to 5 represent the isentropic process and 4 to 5 dash represents the actual process. For a turbine we will define the isentropic efficiency as the actual work divided by the isentropic work. Okay, or the actual heat drop divided by the isentropic heat drop, so that it will become the actual heat drop is T4 minus T5 dash. Okay, we are considering the enthalpy for energies, and if you are considering the Cp value for both air and fuel as same and neglecting the masses, then we can say that mCp dt represents the enthalpy value. Okay, that's why I am using just temperature values. So for the turbine we will define the isentropic efficiency as T4 minus T5 dash divided by T4 minus T5. T4 minus T5. Okay. For the compressor, in the numerator we have the isentropic divided by actual, and for the turbine we have the process as actual divided by isentropic. Okay. This much terms we are required for solving a problem coming in gas turbine cycles.